In this video, we're going to have a look at finding the three different roots of a cubic using the Newton-Raphson method. So the cubic we're going to find the roots of is x cubed plus x squared minus a half x minus a quarter. So what you see there is the graph of y equals that function y equals x cubed plus x squared minus a half x minus a quarter. So in a previous video, we derived the formula for the Newton-Raphson method, which is here. And now we're going to use it in a practical context. So in this case, our f of x is the equation whose roots we're trying to find there. So let's write that down. F of x equals x cubed plus x squared minus 1/2 x minus 1/4. And what we're going to need for the Newton-Raphson method, we're also going to need the differential. We can see here that the formula for the Newton-Raphson method involves the differential of that function. So that implies that f dash x equals 3x squared plus 2x minus 1/2. So this means that the iterative formula that we're going to use is xn plus 1 equals, and look at the formula here, it's xn, I'll zoom out a little bit so you can see the formula still, xn, take, so looking at the formula, we've got f of xn on the top, so f of xn is xn cubed plus xn squared, take, and I'm not going to write half xn, I'm going to write 0.5, I'm going to put it in decimals. I'm just doing that to make it easier to write, to put it on one line. Be easier to type in the calculator as well. Take 0.25. All over f dash xn, which is, we just worked out before, 3 xn squared plus 2 xn, take 0.5. So that's the method we're going to use to solve this equation to find its roots. So we want where x cubed plus x squared minus a half x minus a quarter equals 0. So the first thing we're going to do is choose a start value to use the Newton-Raphson method from. So let's say I want to find this root here, which is roughly minus 1.25. I can see from the diagram. Let's use the Newton-Raphson method to find this root here. So we need to choose a suitable start value. Let's say here. So this is minus 1.1 is going to be my start value. So I'll just mark that on there. So x0 equals minus 1.1. And this is the one I'm going to do in black. So x0 equals minus 1.1. So what I'm going to do now, I'm going to type this Newton-Raphson method into the calculator. I'm going to calculate the first iteration. So I do that by first of all saving our start value, minus 1.1, in the answer button of the calculator. So type minus 1.1 and press equals. And then what I'm going to do is I'm going to type the whole of the right hand side of the equation, so this here, into the calculator, but using the answer button in which I've saved 1.1 instead of xn. So we're subbing in minus 1.1 for xn, and we've saved minus 1.1 in the answer button. So we get answer, that's xn, take fraction, so answer cubed plus answer squared, take 0.5 answer, take 0.25 over 3 answer squared plus 2 answer, take 0.5. And before I press equals, I'm just going to have a look to see what value to expect when I press equals. So what the Newton-Raphson method does, what we did in the proof video earlier, it draws a tangent at this first iterate at x0 equals minus 1.1 and checks for where that tangent crosses the x-axis. So I can see, roughly speaking, I can probably make my tangent a little bit better. Yeah, that's a bit better. So we've got a tangent there and it roughly crosses about minus 1.3. So I would expect my answer when I press equal to be minus 1.3 or thereabouts. Let's see. Yes, almost exactly. So x1 equals minus 1.29247. So x1 equals minus 1.29247. And now, because we've pressed equals, that number's stored in the answer button now. So actually all we have to do to get it back, to get the next iterate, is just press equals again. So minus 1.24. So what it's done here, I'm just going to get rid of that circle there. It's then, from where it crossed the axis, and I'll just mark that as x1, from where it's crossed the axis, it's gone back to the curve at that point, drawn another tangent, which is a lot closer to the root, as you can see. It's a lot closer to the root we circled earlier. And we'll keep on going like that until we get the root. So going back down here, we'll press equals again to get minus 1.2445. So x2 equals minus 1.2445. x3 equals minus 1.2406. And basically we can keep going until we start getting exactly the same numbers. So I keep pressing equals now, we're getting exactly the same. We've got it as precisely as we possibly can. Minus 1.240597152 to 9 decimal places, or 10 significant figures. But what about if we choose a different start value? What about if we chose the value, say, minus 0.6 as our start value? So I'm going to use a different colour now. So minus 0.6. So I'm going to go up to the curve, minus 0.6, and draw my tangent. So I should expect to get a value somewhere between minus 0.2 and minus 0.4. So cancel that. Let's put minus 0.6 in there. But I can use my previous working. If I scroll up to the previous, I see I've still got that formula saved in my calculator. So I press equals. I get minus 0.287, which is again roughly what we expected. Minus 0.2871. So drawing a tangent here. Not a very good tangent. Let's improve on that. There we go. And where the tangent crosses the axis, which is here, should be our new guess. So we'll press equals again. We'll want something. We should get something somewhere between minus 0.3 and minus 0.4. There it is, minus 0.3448. So x2 equals minus 0.3448. And we can see the root from the graph is approximately minus 0.35 roughly. So we keep pressing equals. Yeah, it's roughly that until we get the same. So there we go, solved. And the same goes for this. If we chose a start value around this value here, the same sort of convergence would happen. So a word of warning with the Newton-Raphson method though, it's not very good if you choose your start value around stationary points. So let's say we chose 0.2 as our start value. What's going to happen here, and I'll do it in a different colour, red. If I draw a tangent at this point, if it's completely horizontal, if I've managed to get it bob on the stationary point, then it's never going to cut the axis and the Newton-Raphson method is not going to work. If it's got a slightly positive or negative gradient, it's going to take absolutely ages to hit the axis, and therefore the convergence is going to be poor. So let's have a look at 0.2. So 0.2 equals, and sub it in, there we go, 153 over 10, 15.3. equals 10 equals equals. So it's taking a lot more iterations to converge to the root. Still not very many, but a lot more. So beware of the Newton-Raphson method around stationary points. That's pretty much it. An introduction to the Newton-Raphson method and how to perform it in an exam. For more videos like this, go to a-levelmathsrevision.com or subscribe to our YouTube channel.